This is ECE 343 Signals and Systems, Chapter 3, Part 3. Today we're going to take a look at the unit impulse response for discrete time systems. The unit impulse response for discrete time systems will serve the same purpose as it did for continuous time. We'll use it in computing the zero state response. Last time we did the zero input response, and this is our transition function to get us to where we can do the zero state response for those systems described by constant coefficient linear difference equations. So let's go ahead and take a look at this thing called the unit impulse response. As we would expect, the unit impulse response is just how a system, right? We have a system in here, how that system is going to respond to an input that is set equal to a delta function. So our input x of n, we're going to just let be this delta function, delta n. The output y of n then by definition is going to be this thing called the unit impulse response, h of n. If we think about the kind of systems we've been dealing with, we are looking in this particular chapter at linear time invariant discrete systems, and we're looking at those ones that are described by a constant coefficient linear difference equation that, at least in compact form, looks like some q of e acting on y of n, right, being equal to p of e acting on x of n. So that was our compact notation, input-output notation for this discrete time system. If we just adapt that a tiny bit for this input of a delta and know that h comes out, what do we get? We get q of e acting on h of n, right, equals p of e acting on delta n. That's just making the substitutions of x equaling delta and knowing that the resulting y is going to be h. In this particular case, we're going to go ahead and look at causal systems. Those are the ones that we are typically going to be working with as engineers, at least when time is the independent variable. They're the only kind of systems that we can build. So we're going to go ahead and look at a causal system response. So we know for causal systems what? For causal systems, the output can't precede the input, right? And the input happened at 0. And that means that the initial conditions, h of minus n, right, all the way to h of minus 1. All of those initial conditions must be 0. Anything preceding when the input occurred, right? The output had to have been 0 because it's a causal system. And the unit impulse response is, right, the response to a system that was at rest, that was in 0 state, if you will. So no energy was in the system. The energy only comes when n equals 0, when the delta function hits, and all the output values before that time are all 0. We can use these ICs. So we saw last time that we can solve the difference equations recursively, right? We can do that for any input, including a delta function. So we can make a recursive solution to this unit impulse response, just like we had looked at in our previous lecture. So using those initial conditions, using these, and they seem kind of boring, right? Using these initial conditions, ICs, and this idea that x of n was equal to delta n, right? We can recurse. So we can recurse, or we can find a recursion type solution. We can recurse h of n. We can find a recursion solution to our unit impulse response. Let's do a very quick example on this. It's going to suffer the same limitations we talked about as far as recursion solutions before, namely that you have to keep stepping them along forever, and it's not a closed form solution, but it is easy. So as a quick example, let's go ahead and take a look at this idea of e minus 1, right, acting on h of n being equal to e delta n. Now I've already made the substitution x equaling delta and y equaling h. So if we wanted to kind of go back in time, right, we know that this is the same as something like an e minus 1 system acting on y of n, right, being equal to e x of n. That's just the way these substitutions ended up working out. When we're finding the impulse response h, it requires x be a delta. And so while I didn't explicitly show it there, we could easily get the original difference equation by just substituting in the other direction, right? Making h go back to y and making delta go back to x. Well, let's stick with that response. That is the unit impulse response. In this particular case, we know that also, right, that h of minus 1 is equal to 0. This is a first order system. The highest power of E, right? The largest advance is 1, so it's a first order system. So we only need one initial condition in order to be able to work with this one. Now, if I go ahead and I take that expression, and I'm going to go ahead and return back to that expression, and I expand it out, right? Get it out of the operator form to maybe something just a little more direct, we get something like this. We get h of n plus 1 minus h of n equals delta n plus 1. Now again, nothing wrong with this expression. I just think that it's not going to be the most convenient one because it is in advance form. We talked about this difference between advance and delay form. This book tends to use advance form for comparisons back to chapter 2, but the delay form is more reflective of how we actually carry out operations. So I would like to go ahead and make this in delay form. So I'm going to delay the whole thing, right? I'm going to delay it. Delay by 1. And that's going to make it look like an h of n plus 1 just gets delayed down to h of n. And I'm going to have a minus h of n minus 1, right, equals delta n, something along those lines. Okay, so now I have a delay form difference equation that is expressing this desired quantity, the impulse response h, in terms of this input, the delta function input. What I can do now is I can just solve for h of n, right? H of n is equal to h of n minus 1 plus delta n. This sets up the equation I need to carry out the recursion. If you wanted, you could make a table here, right? And we could start recursing values for different values of n. For example, I'm going to start out at n equaling 0, and that's going to tell me h of 0 is equal to h of minus 1, which we knew because it was a causal system, right? Because this thing was a causal system, we know that that was 0, right? That was the IC, plus delta of 0, and we know delta 0, right, is equal to 1. That's the only time a delta function is non-zero, is when its argument is 0. So this whole thing is going to give me a value 1. At n equals 1, right, h of 1 is equal to h of 0 plus delta of 1. Now, h of 0, right, we are going to grab that value that I had done before. That's the point of this recursion. And I'm going to plug it into that needed next step. And then I'm going to add to that delta 1, which turns out to go to 0 again, right, because delta functions are non-zero only at a single point. So again, we're going to get a value 1. Now, it turns out this is a really simple system. So going on step 2 and further, we get things like h of 2, right, going to be equal to h of 1, which is again 1 plus delta 2, which is again 0, which is 1. In this particular case, we can see that this thing just sits at 1. So while I'm doing recursion in this case, and recursion doesn't normally provide an easy mechanism to get a closed form solution, this one turns out to be so easy that we can recognize the pattern, and we probably could get a closed form solution. So we see the pattern, we see the pattern, we see the pattern, we see the pattern, right? And we get this idea that h of n is something that was 0 before n equaling 0 and it's 1 after. Well, that's just the unit step function, right? So this guy happens to have a unit step function, unit impulse response. It's not always so easy to see the pattern, right? It's pretty rare, actually. So I'm going to just say it's pretty rare. It's pretty rare to see the kind of closed form solution from our recursion, That's a hard thing to see. I think in general, it's not something that is just obvious or one that would become easy to recognize, especially as system orders get higher, right? And so we would like to seek a closed form solution. So it's probably better, right? It's better if we have a mechanism to determine h of n in closed form, right? A closed form, non-recursive solution to that unit impulse response, okay? All right. What does h of n look like? So if I want to think about what's the closed form, right? What's the expected form? of hn, right? I think we could do it something like this. H of n will equal something. Let's think about what happens. H of n is the response to a delta function. A delta function has a non-zero input only at 0, right? And then it backs off, just like continuous time, right? Once it backs off, energy's been stuffed in the system, and the system goes ahead and does what it normally does. And we studied that last lecture. We know that that zero input response looks like a combination of modes. So there should be some combo of modes, right? Combo of modes going on in here. We know that because the delta function puts an energy at 0, right? And a system can respond as a combination of modes to that energy. So because that energy wasn't put in until 0, that combo of modes can't come out until 0. So we'll also throw on that U of n type term. What else can go on in here? Well, because there is an input at 0, right, and systems can act like wires, you could make a digital wire, you could say y equals x. It is possible that the system can allow a delta function through. So there could be some delta type term in there. This is the same kind of conclusion that we had for the continuous time case. We said that there could be a delta plus some sort of combination of modes that look like that zero input response made causal with a U of n. We then just gave the particulars of that form and went about solving it based on those particulars. The particulars were proven in the book. We're going to do something similar here, but we will notice that the form, the particulars of this are going to look slightly different. Okay, so I'm going to just say refer to the book. So proof in book for the exact form that we're going to be laying out here. Part of the reason I don't really like deriving it here is because the time domain is just the wrong place in my mind to derive this particular result. It's not intuitive, it's kind of awkward, and we can get the exact same result later when we go to transform domain for much less effort. So if all we're trying to do with that proof is show that it is actually true, if you can't wait to see that, read the time domain proof in the book. But if you can just be a little bit patient, we will get exactly the same solution through a transform domain approach, and it will require just a far less amount of effort. So what does it look like? H of n, it is going to have this form that we expected. It's going to have that delta term only if bn by an, right, is non-zero. So there's a bn by an delta n in here. If you compare that to the continuous time, it had a different coefficient pattern out front. And so we do have to be a little careful. This discrete time unit impulse response, H of n, is going to have a slightly different form. The particulars of it are slightly different than what we saw in continuous time. So you're going to have to, commit a different guided memory. The other one I'm going to say is that we're going to have a y tilde zir of n made causal U of n, okay? You'll notice that we don't put a PD on this one. And part of the reason for that is because of the way we are going to find our y tilde. We're not going to find it through that set of special initial conditions, which were kind of hard to figure out where they came from, like we did in continuous time. Instead, what we're going to do is we're going to recurse a solution. We will find those coefficients for y tilde zir through recursion, which we already know is a rather simple operation. So you can look at this thing. We know, right? We know this. This is known, right? And this YZR is half known, right? It's half known. Those are the gammas, the characteristic roots, and it's half unknown, right? Half unknown. And that's the coefficients, the C's, right? So how do we find those unknown coefficients? If I want to find those unknown coefficients, I'm going to just do a recursion. I'm going to get n equations in these n unknowns, right, through recursion. In other words, I can recurse values of h of 0, h of 1, h of 2, all the way up to h of n minus 1, right? That gives me a total of cap n equations. And if I recurse the values and then compare them to this closed form solution, I will have n equations in the n unknowns, the C's. Okay, so I think that the probably best way to show this is to do it by example. So let's go ahead and do an example to demonstrate how this would work. I'm going to pick something a little bit more difficult than what we saw in the last example, something that's not quite so trivial, something that would not be quite so easy to find the closed form solution just through recursion by itself. And we'll go ahead and see where we get with it. So let's try this. Let's do an e squared minus 1/4 acting on y of n being equal to e minus 1/3, right, acting on x of n, okay? And I want, so we're going to determine, let's determine the corresponding, right, the corresponding h of n, find that unit impulse response in this case. What do we know? We know from our previous discussion that a closed form solution, h of n, right, is bn by an delta n. And then we are going to have, in this particular case, a plus, something that looks like a zero input response. I put a tilde on there because we find the coefficients through recursion evaluation of this h of n. So y tilde of n made causal u of n, something along those lines. What are my coefficients bn and an? These are where you have to pay attention again to the notational conventions used in these difference equations. And it turns out bn and an are those values the farthest away from the positive powers of e. So we have here, right, this guy here is going to be my a2, and this here is going to be my b2, and we see here that n equals 2. Right? It's a second order difference equation, thus the reason of saying cap n equaling 2. We know it's going to support two modes, right? And just by the convention in here, right? The coefficient that led e squared for the output term, that was my a0, and then they just kept increasing in the coefficient subscript until I got to the last term. That was my a sub n. So in this particular case, I think we can read this off pretty easy, right? If we look at b sub n by a sub n, b sub n is minus 1/3, a sub n is minus 1/4, and if I go ahead and do that, I get 4/3. So in this particular example, for this particular system, there will be a delta function present in that h of n, okay? So we've got that part of it. The next part that we need to do is we need to figure out what is the form of that zero input response, right? So what is the form of that zero input response? We know generally, right, that the zero input response, right, is a linear combination of modes. So it's something like a C1 gamma 1 to the n plus some C2 gamma 2 to the n, and we know that's true if right, gamma 1 does not equal gamma 2, something along those lines. So I do need to find these roots to make sure that this is the form we're looking for, and I know I can get those roots from the characteristic polynomial, set it equal to 0, that's the characteristic equation, find the roots, okay? So I'm going to go back up here, and I'm going to take a look. Here is my q of e, right? I just need to grab that. That's e squared minus 1/4. So replace e with gamma, so I'm going to have q of gamma, right? That's going to be gamma squared minus 1/4. I'll set it equal to 0. That's my characteristic equation. Work a little bit with that. That's a gamma squared equaling to 1/4. So I'm looking for the square roots of 1/4. We can do that in our heads. We know gamma 1, for example, is going to be equal to 1/2, something like that, and gamma 2 is equal to minus 1/2. So I have a pair of roots here, right? 1/2 and a minus 1/2. The corresponding characteristic modes, right, are going to be stuff like gamma 1 to the n, right, which is going to be something like a 1/2 to the n, and the other one's going to be like a gamma 2 to the n. That's like a minus 1/2 to the n. Something may be worth noting here. If you look at these roots, right, and if you thought about these for continuous time, if those had been continuous time, right, if, right, it had been continuous time, we would have had stuff like this. We would have had an e to that root t, right? So we would have had something like e to the t by 2, and we would have had an e to the minus t by 2. This one off here on the right that I call gamma 2 would seem okay. It would be a decaying exponential. This one over here on the right would seem pretty bad, right? So I'll put an x there. It would seem pretty bad because it would seem like it was growing exponentially. These roots in discrete time are
kind of different though, right? Because they are not put in that exponential form. It's just the number raised to the power. And if you look at 1/2 to the n, for example, what kind of values do you get? You get 1, you get 1/2, right? You get 1/4, you get 1/8, and so forth. You just take that power raised to the n, so this would be my n equaling 0 case, something like that. And we can clearly see that decays. Same thing with the other one, the -1/2. That's going to give me a 1 and a -1/2 and a 1/4 and a -1/8, something like that. And that one's also decaying. So what's important here, right, is not that the roots are in the left half plane. That was the rule for continuous time. What's important here for issues of stability, right, for issues that these have modes that will bleed the energy away rather than growing without bound and causing things to break, is that we need the magnitude of gamma to be less than 1. That's going to be what's going to guarantee that these guys have that kind of good behavior. So just a note to kind of keep in mind that our conditions for what might be considered good roots, right? Those that give us kind of well-defined or appropriate system behavior, stuff that doesn't blow up, is going to look a little different than it did in continuous time. Okay, so I've got my two characteristic roots. Now I think I've got everything I need in order to get the overall form for the unit impulse response. So we said h of n was that bn by an delta n. We had already computed that bn by an, right? That was 4/3. So we know we're going to get here a 4/3 delta n. And then we know that we're going to have something that looks like that zero input response, which we said was a C1 tilde gamma 1, right, which is a 1/2 to the n, plus some C2 tilde. They were unique roots, so I don't need any kind of special correction for a repeated root. And I'm going to get a C2 tilde minus 1/2 to the n, right? This whole thing made causal, U of n. So I have a pretty good idea of the general form of this thing, right? I know what it looks like. I just need to find out these particular values, C1 tilde and C2 tilde. So how do I get them? Well, one way I could get them right is if I just knew a couple of values of Hn for which those C values were present. And so if you take a look, that Un doesn't allow those C values to come in until n greater than or equal to 0. So if I can recurse some values like H of 0 or H of 1, I should be able to get two equations, right, and then solve for those two unknowns. In order for me to recurse that number of values of Hn, I need to return back to my original difference equation. So I'm going to go back and I'm going to think now about the recursion. So this is going to be the recursion to get H0 and H1 so I can solve, right? I can solve for C1 tilde and C2 tilde, something along those lines. How do I do that recursion? I go back to the original difference equation. That was E squared, right, minus 1/4 acting on Y. But if I am looking at the unit impulse response, I can replace Y with H, and I know that that's going to be my E minus 1/3 acting not on X, but on delta, because I'm just letting X equal delta, and what comes out is H. If I write this in delay form, right, what do I get? I get H of n minus 1/4 H of n minus 2 equals, right, and I'm going to get a delta n minus 1 minus 1/3 delta n minus 2. Now I just solve for H of n. That sets up the recursion equation. So I will have H of n, right, being equal to 1/4 H of n minus 2, right? And I'm going to have a plus delta n minus 1 and a minus 1/3 delta n minus 2. Notice when I set up this recursion equation, right, it did utilize that polynomial p, right? That's embedded inside this part of the recursion. And that's how those coefficients C1 and C2 are going to reflect that p. It's just gotten in a little different way than we did it in continuous time. Okay, so I have a recursion relationship. Now I just need to recurse some values. How do I do that? I know that this is a causal system, so I'm going to use, right, I'm going to use y of minus 2, not y, h, right? This is my unit impulse response. H of minus 2 equaling h of minus 1 equaling 0. Again, how do I say that? H is the unit impulse response. This is the response of an at-rest system
in response to a delta function. A delta function hits at 0 because it was at rest. Nothing could have been coming out until that input came. So all values of h before 0 are 0, right? We know that. So I'm going to go ahead and just use that set of initial conditions that come naturally out of having a causal system and looking at an impulse response. And now I'm going to go ahead and set up my table and recurse a few values. So I'm going to go ahead and set up this table and look at some values of n. I only need 2 of them, 0 and 1. And I'm going to be solving for what? I'm going to be solving for these values of h of n. So if I look at this, I'm going to have h of 0 is the first one. That's going to be equal to, and I'm going to have 1/4 h of minus 2, right? Plus, I'm going to have delta of minus 1 minus 1/3 delta of, nope, minus 2, something along those lines. Now, this is sort of an interesting one because we already knew that h of minus 2 was 0. That was the causality condition. Delta of minus 1 is also 0. That hasn't hit where delta is not 0. And delta of minus 2 is 0. So that's also going to be 0. And what I get out of all of this stuff, right, is I get a big fat 0. So h of 0 is equal to 0. And even though it's 0, it's going to be enough to help us find one of those coefficients. I'm going to go back now and just do the second one in here. So if I do the second condition, that's going to be h of 1. That's going to be 1/4. H of 1 minus 2 is going to be h of minus 1, right? And then I'm going to have a plus delta of 0 because I have 1 minus 1, right? And I'm going to have a minus 1/3, and I'm going to have a delta of minus 1. If I go ahead and take a look at what all of these guys' values are, again, because it was a causal system, h of minus 1 is 0, right? Delta 0 is going to be equal to 1, and delta minus 1 is 0 again. So this whole thing equals 1. So I've used my recursion, right, to find some values of h. So I know, therefore, that h of 0 equals 0, and h of 1 equals 1. That was grade school mathematics using recursion to find a couple of values. And I'm going to use those two values now in context with this original equation that I'm trying to find, this closed formed equation, right? I'm going to take it and put it into this guy and solve for those unknown coefficients. Let me just go ahead and grab this. I'm going to make a copy that will simplify things. So I'm going to go ahead and copy this thing over, and we'll come down here and repaste it. Repaste it out so we can see that guy. So here's the equation we're trying to do, right? And what I would like to do in this particular case is I'd like to use these initial conditions. So what can I do here? I can say h of 0, which we calculated as 0, is going to be equal to 4/3 delta 0, right? Just following the right-hand side of that closed form expression. And I'm going to have a plus C1 delta. 1/2 to the 0 is just 1, right? I'm going to have a plus C2 tilde, and that's going to have a minus 1/2 to the 0, so that's also a 1. And that whole thing got multiplied by u of 0, which is also 1. So I'm going to just clean this all up. That 0 equals, delta 0 is 1, so I'm going to get a 4/3 plus C1 tilde plus C2 tilde. One equation, two unknowns right now. If I use the second value I recursed, h of 1, we know that that was equal to, if we go back up there, it was a 1 value, right, is equal to 1. That's going to be 4/3 delta 1 plus, we're going to have C1 1/2 to the 1, right, plus C2 tilde minus 1/2 to the 1. Both of those guys times a u of 1, which are both 1s in those cases. I don't have to put that in because 1 times anything just gives us those pieces. This first delta function, right, no longer is on, so that's going to go to 0. And if I just clean this guy up a bit, I get 1 equaling, right, 1/2 c tilde of 1, right, minus 1/2 c tilde 2. So now I've got two equations. Here's one of them. Here's the other one. Two equations, two unknowns, and it's linear in those unknowns. We should be able to solve that guy. I'm going to do just a tiny bit more cleanup on this thing, and I should be good to go. If I bring the 4/3, right, on that equation to the other side, I'm going to get something like this. I'm going to get C1 tilde plus C2 tilde equals minus 4/3. Second one was going to be, it was in terms of a half. Let's just multiply the whole equation by 2, right? That's going to give me a C1 tilde minus C2 tilde equaling 2. something along those lines. Now I could set this up matrix form, right? I could go something like 1 and 1 and 1 and minus 1. That wasn't a very good minus 1. Let's try it again. Minus 1, acting on my coefficient vector C1, C2, both with tildes, right, being equal to this observation vector minus 4/3 and 2, something like that. I could certainly do that and solve it in the standard linear algebra way, but I've already got something that's pretty close here. I see the first equation there has a C 2 tilde, and the second one has a minus C2 tilde. So if I just add those guys, I'm going to be able to solve for C1 really quickly. So I'm going to have 2 C1 tilde being equal to 2 minus 4/3, right? And that's going to be 6/3 minus 4/3. That's 2/3. 2/3, something like that. Divide both sides by 2, and I get a C1 tilde being equal to 1/3 in this particular case, right? Now I just need to go ahead and put that value into one of those two expressions. It doesn't really matter. Take that guy, I'm going to put it into the top one. I'm going to have 1/3 plus C2 tilde equals minus 4/3. Subtract a third from both sides, and what do we get? We get C2. Let's actually do this. In the regular pen here, C2 tilde is equal to minus 4/3 minus a third is minus 5/3, right? By doing that substitution. Now I've got every single piece that I need. I can complete this thing out, and I can see that h of n is equal to 4/3 delta n. That was completely determined from the difference equation coefficients, plus in here, and I knew I had a 1/2 to the n term, and I knew I had a minus 1/2 to the n term. Those are my characteristic modes, also determined from the difference equation. This whole thing has to be made causal. There's the un, and I just need to plug in my coefficients. So I'm going to have a 1/3, right, and a minus 5/3, something like that, and I am done. I've got this nice closed form solution for my unit impulse response. This is a pretty easy process. It's one that can be, easily extended to whatever order system you have, and in general, it's something that can be found just following a really basic set of process steps. And so there's a relatively low likelihood of error if you just are a little bit careful about tracking the details. Okay. So what have we done so far? In earlier lectures, we took a look at a particular class of discrete time systems, those that are described by constant coefficient linear difference equations. Just like the continuous time analog of constant coefficient linear differential equations, we wanted to be able to solve these guys, and the way we ended up deciding to solve it was to break it into two parts based on where the energy came from in the system, either internally, right? So you have initial conditions, no input, that is the zero input response, or externally, right? So you apply an input, but you have the system at rest at zero state, and so that is the zero state response. We solved the zero input response first, found it was a linear combination of modes. We found the modes from the characteristic polynomial, the characteristic equation, found those characteristic roots. So our zero input response was just a linear combination of characteristic modes. We found the coefficients from the initial conditions. We're now working our way towards a zero state response. We're following a similar process to what we did back in continuous time. We're finding this bridging function, this thing called the unit impulse response. So I pull out my hammer, I whack the system, that stuffs energy into the system, and we see what comes out. When you whack the system with a hammer, right, it will respond with modes after that point. So you can have some combination of modes starting at zero, and it could also potentially let that delta through. So you might have an additional delta term in there. So we knew that we could get a closed form solution for this unit impulse response h of n. We know how to get it, right? We've gone through the steps on that. And we also know that we have some other tools for solving these difference equations. We looked at the recursion, although the recursion has the disadvantage that it usually does not end in having, that kind of closed form nature. Okay, so how are we going to use h of n? How do we use h of n to find this thing called the zero state response? I would like to go through a derivation of the zero state response expression, just like we did in continuous time. And how it's going to start is it's going to start with a form of the sifting property, but discrete style. So all of this, if you want to think about it, is going to be working towards the zero state response. That's the other half of this process or this solution to this constant coefficient linear difference equations. And what I would like to do is I'd like to look at, so we're going to go ahead and look at, let's go ahead and look at a discrete time version of the sifting whoops, that's not such good spelling. Let's try that again. Of the sifting property. Let's do a quick reminder. In continuous time, what was the sifting property? It said any old signal x of t could be written as an integral minus infinity to infinity x of tau, right? And I had delta t minus tau d tau. If I break this up into more natural language, right, we say a signal, right? A signal is equal to a sum, and we have some scaled, right? And then we had some shifted deltas, something along those lines. In continuous time, I think this is a little bit hard to visualize. It's a little hard to believe this. We ended up having to use the properties of that direct delta function, which is not a practically realizable function. It's really hard to visualize sums in this limit as an integral. So all of that makes the sifting property in continuous time pretty difficult. Let's think about this equation's description, though. A signal is a sum of scaled and shifted delta functions. And let's look at it in the context of a discrete time signal. So I'm going to go ahead and look at a signal that is a function of n, the discrete time variable, and I'm just going to call this guy x of n. And I'm going to go in here and I'm going to plot something out. So it's going to have some value at 0 and something, and something, and something, and something, and something, and maybe something back here and another one up there, and then I'm going to just let it be zeros or something like that. Okay, so there's a typical discrete time signal. Let's take a look at what this sifting properties equation description says. It says we can represent a signal, right? Here's my signal, that blue guy, right? As a sum of some scaled and shifted deltas. So let's first look. Does this look like a bunch of deltas, right? Does that thing look like a bunch of deltas? Well, sure it does. If you take a look at that, there's one delta, there's a delta, there's a delta. They're just all shifted by some amount, some integer amount, right? So a discrete time signal automatically looks like a bunch of shifted deltas. Are they scaled together? Well, sure, they're scaled together, right? If I look at the scaling factor here, there's all these different scale factors. What's the scale factor at any particular point? It's whatever the value of the function is at that point. So the scale factor here is x of 0, right? The scale factor on this one is x of 2, because I skipped that first one. It was of height 0. X3, and then here's like x of 4, something like that. So I just have some particular value, some amount, right? Scaling a particular delta function. What is that delta function? That's a delta of n minus 4. It's the delta function at 4. If I scale, right, take x of 4 times delta n minus 4, I get this overall piece. And then if I do that for every single one of them, sum them all up, I get the overall response. So the sifting property for discrete time is almost self-evident, right? It is not a mystery. It's nothing that you can't visualize. It is actually just completely obvious when you draw out a discrete time signal. So the discrete time sifting property is not one of any particular mystery. It says our discrete time signal can be thought of as a summation. Let's do that sum on some variable k going from minus infinity to infinity. I'm going to have my scale factors, x of k, and delta n minus k, right? I just have a bunch of shifted delta functions scaled by the particular amount at that instant, right? Okay, so that's the discrete time sifting property. If you break that out term by term, you can easily verify that above graph. What am I going to do with that? I'm going to utilize this in the same way that I use the sifting property for continuous time in order to try to derive this idea of the zero state response. I'm going to do it a little different. We could do it both ways. Maybe I'll do it both ways, but let's do it a little different. So here are some things we know. Okay, so let's just do a logical progression here. I know that a delta function, right, going through a system creates the unit impulse response. No problem. What else do I know? I know that a delta function shifted, right, just gives me that unit impulse response, shifted. How do I know that? Because it's a time invariant system, right? So time invariant says that a shift in the input just gives me a shift in the output. No problem. So that's not a particular issue. Next thing I could do, I could scale that delta. I could take some value, x of k, let's call it, multiply it by that time domain function, delta n, that's been shifted, so minus k. And what comes out then? Well, linearity tells me it's the same scale factor times the other guy, h of n minus k, right? So this is part of linearity, right? This is the homogeneity or the scaling part. So we could think of this as the scaling or homogeneity part of linearity, right? That I can scale some input and I'll just get a scale in the output. I also know that linearity has another part, right? Linearity is the next part. Linearity not only has a scaling part, but it has a summing part. So I could do that for a bunch of different values of k. So I could sum up over an infinite number of k's and add those all together, and I would get the same thing on the output. So I'm going to have a sum k going from minus infinity to infinity of x of k delta n minus k, right? Linearity says that that's just going to give me the same linear combination. So a sum from k going from minus infinity to infinity of now the responses x of k h of n minus k, right? But what do I see here on the left? This guy looks familiar. That, right, from the discrete time sifting property is just x of n. So x of n going through my system, you have a general input going into my system. I know the output is y of n, so this piece must be y of n, right? And we can see that that equals a sum on k minus infinity to infinity, x of k, right, h of n minus k. This is such an important result, it deserves its own kind of repetition. So I'm going to clean it up and make sure that we've got it all neatly done out. So what did we have? We had x of n is my input, which a discrete time sifting says we could represent as a sum, k equaling minus infinity to infinity of some x of k, right? And I had delta n minus k. I'm going to apply this thing to my system, and it's going to generate an output, which I showed just through a logical sequence of steps that use the properties of linearity and time invariance, both properties that we know to be true for a constant coefficient linear difference equation. And we found that that y of n had to be a summation, k equaling minus infinity to infinity, right? X of k, and now instead of delta, we had h of n minus k. What was the English language description of the sifting, right? My input was equal to a sum of scaled, sum of scaled, right? And then shifted deltas, right? What does this other one say? It says my output is equal to the same sum, same scale, so sum of scaled, right? Responses to deltas. And I should have said scaled and shifted responses to delta. So an input is represented as a sum of scaled and shifted deltas, and the output is the same sum of scaled and shifted responses to those deltas. This is precisely the property that we saw for continuous time. It's precisely the same structure that we saw for continuous time. It's just in continuous time we had an integral, right? And here in discrete time we have a summation, which makes sense because discrete time signals can't support integrals. Instead, we need summations. This guy, this summation here describing the output, right, is going to be, this is our zero state response as described by something called the convolution sum. So the zero state response can be found, right, by the convolution sum. Y of n equals a summation minus infinity to infinity x of k h of n minus k. If I know my input x and I know the unit impulse response, that single measurement, pull out your hammer, whack the system, see what comes out. If you know those two pieces of information, you can determine the system output. That unit impulse response completely characterizes, right, the behavior of that system. So what do we see on this? If you know, right, if you know h of n for, right, this linear time invariant discrete system, right, you will know, and that's through the convolution, and I'll put sum here just to emphasize that, through the convolution sum, right, the response to any input. H of n is enough, right, to fully understand the linear time invariant discrete system zero state response, right? It's output in response to an input. If you know h of n, you can get the output just by knowing the input that's going in and using that single measurement of the system. Beautiful result. Next lecture, we're going to focus on solving this convolution sum. A lot of it's going to look familiar, but because it's discrete time, we're going to have some other options available to us, much like we had some other options in finding the zero input response, right? We used recursion, for example. So in this discrete time case, we'll have some other options for doing the convolution sum as well. That will be next time.